Welcome back, chemists. So let's dive into chapter 2, entitled Atoms, Molecules, and Ions. So these topics are more closely related to actual chemistry that we will use as chemists. So here's the outline of the chapter. The first couple sections has to do with history of chemistry, so it sets the stage for modern day chemistry where we're at right now. And then the second half of the chapter has to do more with chemical symbols and the symbolic domains of chemistry. So elemental symbols, chemical symbols that you see on the periodic table to signify substances that we will use within this course. All right, so let's get started with atoms. So really the concept of atoms didn't come from a chemist. So over 2,000 years ago, this was theorized by philosophers. So a bunch of philosophers like Aristotle, Plato, they were sitting under, an olive tree, just thinking about things, thinking about life, and someone may have asked another person or asked themselves, okay, what if we took an object and kept cutting it, cutting it until you could not cut it anymore? And that concept of being able to divide something so much before it's no longer that thing anymore brought about the concept of an atom. We know that elements off of the periodic table are composed of atoms. So this concept came about by philosophers. And then over time, we brought in, the scientific method and started testing things. And then from that was born modern day chemistry. And so we'll talk about some of the chemists that took these concepts, these philosophical concepts, and then turned them more into the scientific realm. Okay. So, and one of those chemists is John Dalton. So, in the early 1800s, he was the first to really recognize the atomic theory, modern day atomic theory. And we'll go over his four postulates here. So, Dalton's four postulates of the atomic theory. And so, those four postulates that he came up with in the 1800s still mainly hold true today. And so, we'll talk about them. So, the first one of his postulates, so the tiers, the basis of his atomic theory, his idea is that each element is composed of extremely small particles called atoms. All right, so we can have an atom of the element oxygen or an atom of the element nitrogen. All right, and then second postulate showed how atoms can be different. So all atoms of a given element, so the element oxygen, are identical, but atoms of a different element are different. So what do I want to see here? The atoms of one element are different from the atoms of a different element. And I'll know it's a lot of experimentation and observations that he was able to put together these postulates, this theory. Okay. Oh, and then I have a picture here. So we have, multiple atoms of oxygen. This element, all these atoms are identical. And then we have a different substance, a different element, nitrogen. All of those atoms are the same in one another, but an oxygen atom is different than a nitrogen atom. Okay. His third postulate says that atoms of one element cannot be changed into atoms of a different element. So we can't turn elements into something else. I mean, a lot of the basis of chemistry was trying to synthesize gold. Can we make gold from other substances? And they found out, no, you can't. Because of this third postulate, we can't take atoms of one element and change them into a different one. Can't turn them into a different one by chemical reactions. And so another way we could say this is that atoms cannot be created or destroyed in a chemical reaction. And really what this is the conservation of mass, the law of conservation of mass that we've talked about in the previous chapter, conservation of mass. Great. All right, and then finally, his fourth postulate. Oh, yeah, so oxygen cannot turn into nitrogen. We can't take lead and turn it into gold, unfortunately. And that was the basis of alchemy. And finally, his last postulate is compounds are formed when atoms of more than one element combine, and a given compound always has the same relative number and type and the same relative number and kind of atom or type of atom. And what this is essentially is the law of constant composition, which we've talked about composition before. Like water always has two hydrogens and one oxygen. The water that you drink at your house is the same water that I drink at my house. It all is composed of molecules that have the chemical formula H2O. Right? And so in this example, we can chemically combine a nitrogen atom and an oxygen atom to form the compound NO, so that substance. All NO compounds have the same relative number of nitrogens and oxygens within that sample. They will always look like this: one nitrogen, one oxygen in that compound. So the four postulates that we just talked about form the basis of Dalton's atomic theory. Each one of those postulates is an explanation for some type of chemical phenomena that either he or another chemist had observed. And back when he made these explanations back in the 1800s, no one could disprove it. No one observed some type of chemical reaction that went against any of those postulates, like the law of conservation of mass. No one had witnessed something or observed something that went against that. So since it couldn't be disproven, it was accepted as a theory. Remember, theories are just explanations. So these four postulates are just explanations for chemical observations that chemists make. And so, surprisingly, his atomic theory pretty much holds true today, even 200 years later. Most things remain consistent today, except a couple things. So, by the mid 1800s, there were some observations that went against his atomic theory, and those are the things we're going to talk about in the next slides: subatomic particles. So those observations that actually went against his explanation were that some experiments that other chemists did indicated that atoms were in fact divisible, that you could make them smaller. And we'll learn about the components of an atom. That's where it comes from. And so this was evidence for the existence of subatomic particles. So Dalton's atomic theory does not state or explain the existence of subatomic particles, but Dalton's theory does explain a lot of things with chemical reactions. All right, so now let's talk about atomic structure and those subatomic particles, the components that make up an atom. So a subatomic particle are particles that are smaller than a single atom. And let's just talk about those three things here. So the three subatomic particles that we will talk about in this course at length are protons, electrons, and neutrons. Right? So those three subatomic particles, these compose an atom, or they make up an atom. Compose an atom. All right, and we'll talk about the experiments and the events that led to the discovery of these three subatomic particles. So I'll take note that the first subatomic particle that was discovered was the electron. All right, so electrons have a negative charge, and that was something that they were able to take advantage of in order to discover it. The next subatomic particle discovered was the proton. Again, protons have a positive charge, so they were able to observe that. And the last thing that the last subatomic particle discovered, and pretty late, by the way, was the neutron. So this was the third one. Discovered. Neutrons are neutral. They only have mass, so it was harder to detect with the instrumentation they had at the time. Okay, so let's talk about the events that led to the discovery of the first subatomic particle in our list, or the first one discovered, which was the electron. So the electron was discovered by use of a cathode ray tube, which I have a picture of right here. So a cathode ray tube, and I explain it up here in words, but a cathode ray tube is essentially just an evacuated cylinder. So evacuated meaning there's no pressure on the inside, so there's no atoms, there's no gas or anything on the inside. And then on either end of the evacuated glass are electrodes. So what they did in the experiment was they sent a high voltage or electricity through the evacuated glass through the cathode ray tube. And what they saw when they put a fluorescent background on the tube, they saw a bright light come up when they put electricity through it. And what they were actually seeing were electrons. All right. And so a couple things happen. So you see that we have like a stream of electrons coming from the cathode. And that's why they call it a cathode ray tube, because the discharge was coming from the cathode, going to the anode. So the phosphorescent strip within the tube was just so you were able to see the electrons. So that's what you see here is the stream of electrons going from either electrode. And so the actual experiment was to use a magnetic field, to bend the electron stream, the discharge. And it was that experimentation that led to the discovery of the electron and some of the properties that have to do with electrons. And so these are the observations of the cathode ray tube experiment. So the actual experiment was, sending a high voltage electrical current through the tube, and then using a magnet to deflect the stream of electrons. This part is the actual experiment, right? And so what they saw when they sent electricity through the cathode ray tube was that the ray, or the stream of electrons, but they didn't know they were electrons then, the stream that they saw traveled in a straight line. So that was one of the observations. Then some of these other observations let them make some conclusions about what they were seeing. So the second observation is that you can bend the stream that they saw up here using a magnet or some type of magnetic field or electric field. And the way the stream bent indicated that the stream of particles were, in fact, negatively charged. So if we see up in this picture, we see that the stream of electrons deflects upwards. I should do a different color. Deflects upwards. All right, so this magnet that you see here probably had the positive end here. All right, so they were able to make the conclusion that whatever made up this stream, this light, was negatively charged. What they were seeing was negatively charged because they were using the positive end of the magnet. All right, so if it was the other way, then they would have made the conclusion that it was a different charge, like positive. But the experiment, the observations they made, concluded that those particles, the cathode rays, were in fact negatively charged. Okay, so they also saw other observations. They saw if they put a pinwheel in the path of this ray, should erase this. I guess I can use this one. So if they put a pinwheel in front of essentially inside the tube, they put a little pinwheel inside the tube of evacuated gas on the inside, and they saw that the stream, the ray, would actually turn the pinwheel. So that indicates that they are particles, that they have mass. Particles. So they have to have mass. Right? So like light, for example. Light can't turn a pinwheel. Light doesn't have mass, so it's not a particle. But what they were seeing, although it looks like light, could in fact turn a pinwheel. So that's something different that's happening. So it could turn a pinwheel. So what they were seeing had mass, in fact had mass, because it can turn a pinwheel. Fourthly, the fourth observation they made is that the cathode ray, the ray that they were seeing going across, heats the tube. So that means that whatever is being emitted, discharging from the cathode ray tube, must be highly energetic. Is that what I want to say? Yes, highly energetic. Must be highly energetic, because the tube gets hot after a while. Oh my gosh, energetic. I can spell. Right? And then finally, the fifth observation they said is that they saw identical results, identical observations, no matter what the material was comprised of the cathode. So the cathode, essentially the metal tips of the tube, it didn't matter what it was made out of, whatever metal it was, copper, iron, whatever, they saw the same results. So that means that this phenomena, whatever is coming out, discharging from the tube, is a fundamental part of all matter. Part of all matter. So essentially what I'm trying to say is that all matter, if you set it up in this contraption, will emit electrons, and that's what they were seeing. They were seeing the flow of electrons from one cathode to the cathode to the anode. So essentially, what they're saying is that all matter has electrons, but of course they were seeing electrons for the first time, so they didn't know. All that they could use were the observations that they made, and so doesn't matter what the cathode was made out of, it would still, this experiment, they made the same observations. And so the conclusion that they made from all of these five observations is that we have electrons. It's the existence of electrons, which are highly energetic, negatively charged, fundamental particles. That was their conclusion. And so you can see how all of these things, this sentence that I just wrote, or whatever partial definition of electron, came from all of these different observations. We have highly energetic, that relates to this observation that it heats the tube. Negatively charged, that was determined by the use of a magnet to deflect the ray. And then fundamental, this will be observed in any type of material. And then finally, particle, because of the little pinwheel experiment they did that turned the pinwheel. And so that was their conclusion for the existence of electrons. So here is another cathode ray tube experiment, this time done by J.J. Thomson. In this experiment, it's a little fancier because in the end, it's more quantitative, meaning that we got some quantities out of this experiment. We got some numbers or values out of it. While this first cathode ray tube experiment was more qualitative, where we got from the, how the experiment was designed, we got some qualities about the electron. We know that it's negatively charged. We know that it's energetic, that it has mass. Like, those are just qualities. While J.J. Thomson's experiment was more quantitative. We got some numbers out of it. It's a little bit fancier, but it still has to do with the cathode ray. So he took essentially a cathode ray tube. He, sent electricity, high voltage through it to make our cathode ray be for the electron path. Same thing as the experiment above. But what he did differently is that he set up both an electric field and a magnetic field around the cathode ray. So he essentially used, let's say, the electric field first to deflect the ray, the electron path, in one direction. And then he took a magnetic field and tried to balance that out. Essentially, could he make the path straight again by turning on a magnetic field? So he essentially balanced the electric field and magnetic field so they cancel each other out to keep that path straight. And so by balancing that out, he was able to calculate a charge to mass ratio of the electron. So that's essentially what you need to get. That the J.J. Thomson's cathode ray tube experiment was a quantitative experiment, and from it he got a charge to mass ratio of the electron. And so the value that he got for the charge to mass ratio of an electron was 1.7588 times 10 to the 8 coulombs per gram. Right? So we never use this value in modern day chemistry. But this was a very important experiment because we were learning about these subatomic particles and some of their properties. But we don't use this value. So J.J. Thomson came up with the charge to mass ratio. So the unit for charge is coulombs, and the unit for mass is grams. So we never use this actual unit in chemistry. So to make it more useful, we need to figure out, well, what is the charge of the electron, or what is the mass of an electron? But this was the first experiment done. So if someone was able to determine either the charge or mass of the electron, we could back calculate and determine the other value. Like if someone figured out the charge, we could use dimensional analysis and figure out the mass of an electron. And that's exactly what happened. So a little bit later, so about 6 years later, about 12 years later, Millikan's oil drop experiment came about. those results. So his experiment, Millikan's oil drop experiment, determined the charge of the electron. So if we know the charge of the electron, we can back calculate, use the charge to mass ratio and dimensional analysis to determine the mass of an electron. Right? So I'll explain Millikan's oil drop experiment. So this is different. It doesn't have to do with a cathode ray tube. But essentially what Millikan did is he took like a spray of oil, like an aerosol of oil, drops of oil, and he sprayed that into this cavity. And as those oil droplets were falling, as the spray of oil dropped, he would irradiate those drops with X-rays. So these really highly energetic electromagnetic radiation. And essentially those oil droplets would pick up negative charge as they fell. So now we have these oil droplets that have a negative charge on them. And so essentially an extra electron on them. And so as those droplets were falling, he set up a voltage between two plates. And he varied the voltage between those two plates in order to catch one of the negatively charged droplets. And so he did this experiment over and over and over, trying to catch these oil droplets in a way where he could just isolate one electron. And so what he saw when doing this experiment is that the negative charge on the drops could be calculated from the voltage that he applied between these two plates when he would catch one of those oil droplets, because essentially it would suspend between the two plates, that he would catch them in such a way. And so what he saw when he calculated the charge on the oil droplets themselves is that a negative charge would always come up. And that negative charge was always a whole number multiple of 1.6022 times 10 to the negative 19 coulombs. So essentially what this means, a whole number multiple, what that means is sometimes there would be one extra electron on the oil droplet, 2, 3, or 4. So essentially he would catch oil droplets that were some multiple of the charge of a single electron. So his conclusion was that the charge of a single electron, because sometimes oil droplets would have 1, 2, 3, 4, 5 extra electrons on it, that the electrical charge of one electron has to be this number, that multiple. So a single electron must have a charge of 1.6022 times 10 to the negative 19 coulombs. Right? So now that Millikan came up with the charge of a single electron, we can now put those together and calculate the mass of an electron. So this is essentially dimensional analysis. We have a charge to mass ratio and the charge of a single electron. So now we can calculate the mass of an electron, because we can turn the charge to mass ratio into an equality. So if we want to turn this unit into an equality, you can just think of it as a derived unit. See, all this always comes back up. So if we take a look at the unit, 1.7 times 10 to the 8 coulombs per gram. It's per 1 gram, because gram is in the denominator, so there's an implied 1 there. So if we wrote out an equality there, we can say 1.7588 times 10 to the 8 coulombs equals 1 gram of electrons. That's how much charge 1 gram of electrons would have. Well, Millikan got the charge of a single electron, which is here. So this is the charge of 1 electron. So if we start with Millikan's number, 1.6022 times 10 to the negative 19 coulombs, and then use J.J. Thomson's charge to mass ratio and set it up in such a way so coulombs cancels. So we'll put J.J. Thomson's value there, 1.7588 times 10 to the 8 coulombs over 1 gram. That's the other side of the equality. So now you can see how those units, coulombs cancels, leaving us with grams. So this will tell us the mass of 1 electron. And that is, the mass of 1 electron is 9.1096 times 10 to the negative 28 grams. So this is the mass of 1 electron. So the conclusion here is that electrons are very, very, very small. If we actually wrote out this number, this mass, we would write 0. and then 27 zeros. So 27 zeros and then 91096. So it's funny that electrons, for being how small they are, were the first subatomic particle discovered. So again, electrons are very, very small. Okay, so this leads us to now talking about radioactivity and how radioactive elements is what helped us discover the other subatomic particles. So electrons were the first subatomic particle discovered, and the experiments that led to those to that discovery are kind of more flamboyant. That they're more interesting. These next ones aren't as interesting. So it's radioactivity that helped us discover protons and neutrons. This work was pioneered by these different chemists, so Henry Becquerel, the Curies, and Ernst Rutherford, who we'll talk about later about atomic structure. So it was radioactive elements that helped us discover these the proton and the neutron. And part of that has to do with the different radiations, alpha particles, beta particles, and gamma rays. And so we'll just define those here. Sometimes these different radioactive particles would be emitted spontaneously from certain radioactive elements. And so alpha particles, so we're using the Greek alphabet here. Just know alpha particles are just positively charged particles. So note that I say particles, so it has mass. Alpha particles have mass. Beta particles are negatively charged particles. Also has mass because I say it has particles. And then finally, gamma rays. So note how I went from particle, particle, ray. So gamma rays are highly energetic, but has no mass. Is that what I'm going to say here? Yeah, no mass or charge. Right, but it's very highly energetic. Come on, energetic. So lots of energy, but no mass or charge. So gamma rays are a little bit different, and so it's these experiments, these radioactivity experiments, led to the discovery of protons. And so protons, they were discovered using kind of like a cathode ray tube. They used evacuated tubes and they filled them with a gas at a very low pressure. So think of like a neon sign. And then essentially they applied a very high voltage to them. And so the hypothesis here is when you made a gas that's within your discharge tube, highly energetic, an electron from the cathode will strike the neutral atom and knock some electrons off. So what essentially is happening, like in a neon sign, where neon is introduced to the gas or introduced to the tube. So there's a low pressure of neon within your neon sign. So we take voltage or electrons, and then we introduce our gas like neon, like a neutral neon atom. Right? And then what this hypothesis says, is that this highly energetic electron will knock an electron off of that neutral neon. So what you'll get in the end is a neon with a positive charge and then 2 electrons off of it. And so they did this with a lot of different gases. So each gas will produce a different colored glow in the discharge tube or in the neon sign. So that's why neon signs glow an intense orange or red, or why fluorescent lights actually have a little bit of mercury in them, because the discharge from mercury gives off what looks like white light. So that is essentially the basis of how a proton was discovered. But instead of using neon, we used hydrogen gas instead. Right? So this kind of gives us a glimpse into it. Because when we use hydrogen, when we knock off an electron off of a hydrogen atom, you just get H+, which is just a single proton. All right, so it was assumed that the hydrogen ion, or H+, was represented, because that's the simplest element, was the fundamental particle of positive charge, which we call a proton. So a single positively charged hydrogen atom is just one proton. And so what they saw is that the proton had a charge that was equal in magnitude of that of an electron, just with positive charge instead. So essentially, they used the J.J. Thomson experiment similarly, but this time just with hydrogen gas. And so the conclusion that they made was that the mass of the proton was 1.6726 times 10 to the 24. So a lot bigger than the mass of an electron. So remember, of the electron, it was to the negative 28. So that means that the mass of a proton was almost 2,000 times greater than that of the mass of an electron. Okay, so that's how the proton was discovered. So not as flashy as the electron. So essentially, they used like a neon sign just filled with hydrogen instead to discover it. All right, and then lastly, the neutron was the last subatomic particle to be discovered, and this was almost 2 decades later, so in the 1930s. And again, this one was the hardest one to discover and isolate because it's neutral. At least in the other subatomic particles, they can utilize charges and electric fields and magnetic fields to deflect the rays or whatever. But neutron, a little bit harder. So they knew that neutrons existed because protons and electrons could only account for some of the mass of an atom. So they knew that there was some more mass in there. So it wasn't until the use of nuclear reactors and the ability to actually do nuclear reactions where we have fission or fusion happening, where we able to actually detect a neutron. So we had to have nuclear reactors in order to do that. And so in the end, the observations they made is that a neutron has zero charge. And because it has zero charge, they're not affected by electric or magnetic fields, so it was a lot harder to find them. And the mass is similar, only slightly more than the mass of a proton. So there's your mass of your neutron, and remember, it has neutral or a zero charge. No charge, right? So just mass. So it's very similar in mass. So for a neutron, it's 1.6749. In a proton, it's 1.6726. So literally, it only is different in the last two places. All right, so it's just slightly more, has more mass. So there are our 3 subatomic particles. So let's kind of just summarize those subatomic particles in terms of mass and charge. So when talking about mass of subatomic particles, we oftentimes use a different unit. So we don't use grams. We'll oftentimes use the unit AMU, which stands for atomic mass unit, where 1 AMU is equal to that of basically the mass of a proton. So 1 AMU is 1.6706 times 10 to the negative 24 grams. And you'll see why we oftentimes use AMU when we talk about molar masses soon and in the next slide. So mass, when talking about subatomic particles, we use the unit AMU. For charge of those subatomic particles, we typically talk about relative charge and not in the charge of coulombs. In chemist talk, we talk about relative charge. So typically, we just say an electron has a -1 charge, a proton has a +1 charge, and a neutron has a 0 charge. But of course, these are reflected in their coulombs. So what the electron has a charge of negative, what did we say it was? Negative 1.6022 times 10 to the negative 19 coulombs. So we just talk about the signage and the relative charge, because the magnitudes of the charges for electrons and protons are the same, just in the different direction. All right, so that is mass and charge for those subatomic particles. So let's just summarize those here. So the symbols we use for electron, proton, neutron, you already see that I symbolize electron as E with a negative sign. The negative sign just reminds you the charge of what an electron is. Same thing with proton. The symbol for proton, we use a lowercase p with a plus subscript, just to remind you that that's a positive subatomic particle. And then neutron is just an n, a lowercase n with, you guessed it, a 0 subscript or superscript to remind you of the charge. And so we see the masses here of each of these subatomic particles in AMU, and you see why we use AMU, because now the mass of a proton is now 1.0073. And the mass of a neutron is 1.0087. So it's closer to 1. Those numbers are nicer to work with than numbers like, 1.6749 times 10 to the negative 24. That's not a nice number to constantly be throwing around. So we typically, chemists and physicists will oftentimes use AMU. And then finally, relative charge, we talk about electrons, -1, protons, +1, neutrons, 0. Okay, so let's finish off this section of history and subatomic particles and think about how those subatomic particles come together to actually form an atom, because atoms are composed of subatomic particles. So now more theories and models come about, and predictions or explanations of what an atom might look like, a single atom might look like. And one of the first models that they came up with is the plum pudding model. Right, so it was really simplistic. So the plum pudding model was really the accepted theory for the atomic structure up until 1910, where we came up with more complex theories of atomic structure. So this plum pudding model was proposed by Thomson in 1904. And so this model just said that, okay, we kind of have like a sphere of positive charge throughout the atom. So that's where like the protons reside. And then we have negatively charged electrons just kind of sprinkled in it, kind of like a chocolate chip cookie. So chocolate chip cookie. Okay, because I don't know what a plum pudding is. They did in England. That's where Thomson was from. So that's why he called it that. But if here in America in modern day times, think of a chocolate chip cookie, all right, where the cookie part, that is your positive charge. That's where the mass of your protons and neutrons are. And then like chocolate chips, you sprinkle your negative electrons around it. Right? So that was the plum pudding model. And that was the accepted theory up until about 1910, where a guy named Ernest Rutherford, essentially debunks J.J. Thomson's plum pudding model with his gold foil experiment. So this experiment was pretty profound. So what Rutherford did in, I guess, 1911 is he took a beam of alpha particles. He made like a gun of alpha particles, and would shoot it at a thin sheet of gold foil and observed what happened. So a really thin sheet of gold foil. He saw that most of the alpha particles went right through the gold foil as if it were like a piece of tissue paper, like you were shooting a gun through a sheet of tissue paper. And so how he set up the experiment, he set up this like screen, this luminescent screen, to detect any alpha particles. So he saw that the majority of the alpha particles went right through. But after the experiment went on for a while, he started seeing little other signals, little other shots of alpha particles show up. So that's what he saw. He saw some of the alpha particles were slightly deflected, so they didn't just go straight through. They went through the gold sheet and went off to the side. And then the most jarring thing that he saw is that some alpha particles were literally bounced right backwards, like back into the gun source, right? And so that was the really profound thing that he observed in his experiment. So what was happening? So since most of the alpha particles went straight through, what scientists and what he concluded is that atoms are mostly empty space. The majority of atoms are empty space. But once in a while, those alpha particles would actually hit something really dense, because some of those alpha particles, essentially you can think like a cannonball, would come straight back and bounce off the gold foil sheet. And so that's what I have here. A small fraction of those alpha particles were deflected back at a large angle, or deflected backwards. And so you can just imagine it's like shooting a cannon at a piece of tissue paper, and then some of those cannonballs just come straight back at you. So that's crazy. And so what they concluded is that the center of an atom, there has to be something in the center of the atom that is very small and very dense. Small because only some of them, only a few of those alpha particles were deflected straight back. So that's why we said it was small. We know that it's very, very dense because it has to be dense enough to actually deflect an alpha particle backwards. So now we have to think, how does that change our atomic model? How does that change the plum pudding, the chocolate chip cookie model? And so this brings us to a more modern day approach to the atomic structure of an atom. Not quite, but closer. So the conclusion that Ernest Rutherford made from his gold foil experiment is that the atom must consist of a very small indents center or nucleus that containing the protons and neutrons and essentially nearly all the mass of the atom. And then the rest of the atom is empty space, and that is where the electrons reside. So the nucleus is surrounded by the electrons that are distributed around the rest of the volume of the atom. And so we typically talk about the size of an atom has a diameter of about 1 angstrom, so 1 times 10 to the negative 10 meters. And so the size of the actual nucleus inside of an atom is even smaller than that, much, much, much smaller, is 1 times 10 to the negative 15 here. So an order of 5 smaller than the atom. So you can kind of think about the atom is 100,000 times larger than a nucleus. So you can kind of think of like a football stadium. A football stadium is like the atom. And then the nucleus is actually like a marble sitting on the 50-yard line. So that's the relative size of the nucleus versus the rest of the atom. Okay, so we've talked about the atomic structure and where the electrons, protons, and neutrons reside in like a pictorial, in a microscopic view of the atom, because although we can't see this with our eyes, I have to represent them in some way of how those different subatomic particles are arranged. So now let's talk about how we can represent the electrons, neutrons, protons of an atom in a symbolic way. And so we can use nuclear symbols, or sometimes we call them nuclide symbols. This is how we can use symbols to represent different isotopes of different elements. So these nuclear symbols that I have like a generic one here, tells us the composition of a nucleus. Composition of a nucleus of an atom. So the parts of a nuclear symbol, so the X component of our nuclear symbol, this is the chemical symbol from the periodic table. So if we were talking about copper, we would put Cu in for X. The subscript down here, this is the atomic number. So the atomic number is indicated by whatever element it is. It's element specific. So on our periodic table, where is mine? Oh no. My periodic table, all right, I'll give everyone this exact periodic table at recitation. Next, our first in-person recitation. So like copper is right here. Copper has an atomic number of 29. So this is element specific. All right, and then finally mass number. Mass number, and we'll talk about all of this. This is the number of protons plus the number of neutrons. This is where all the mass of the element resides, in the protons and neutrons. And so mass number goes up here in the superscript spot. All right, so atomic number Z distinguishes the element. Is that what I want to say here? Yeah, so it distinguishes the element from a different element. So if we were talking about zinc, for example, then we would put a different atomic number, Z. And so what that number represents, Z, so the number here on the periodic table for zinc, it is 30, while for copper, it is 29. All right, Z tells us the number of protons in the nucleus. The atomic number is the number of protons within the nucleus. The number of protons defines what element it is. And just as an aside, if we have a neutral atom, if we know the number of protons in the nucleus, if the atom is neutral, then we have to have an equal number of electrons around the nucleus in order to cancel out that charge to produce a neutral atom. And when we get to ions, we'll learn that, number of electrons can change within an element, but the number of protons never changes for an element for chemical reactions. Right? So that is Z. Z is our atomic number. It defines the element. Mass number is different. Mass number, or A, so the superscript spot, tells us the total number of protons and neutrons within your nucleus. So this is where all the mass is. That's why we call it mass number. So the number that you put in the superscript spot is just the number of protons. So Z, our atomic number, plus the number of neutrons. And that typically has to be told to you or described to you. All right. And so here is an example of a nuclear symbol for nickel. All right. So nickel here on the periodic table next to copper. So it has a atomic number of 28. Right. So nickel has the atomic number of 28. 28 protons. All right. So that's what we could say. The nuclear symbol here is an atom of nickel with 28 protons. All right, so we can get the number of neutrons by subtracting the atomic number, the mass number minus the atomic number. So the number of neutrons here is equal to 59 minus 28, so that equals 31 neutrons. So in general, the number of neutrons in any nuclear symbol is just the mass number minus the atomic number. I'll highlight that. Number of neutrons is the mass number minus the atomic number. And so here we have 31 neutrons. And then our last subatomic particle is our electron. This is a neutral nickel, right? So if it's neutral, the number of electrons must equal the number of protons, so there has to be 28 electrons. Right? So that is within one nickel atom. We can also represent this symbol in a different way. We can call it nickel 59. Mine's weird. 59 or nickel 59. Right? So this is another way to represent it because we know it's nickel. So we know how many protons it has. So you'll write the element name and then the mass number. Because from this number, the mass number, we can always calculate the number of neutrons within it because the number of protons is given by the actual element. All right, so now let's think about different isotopes. There are different nickels that have a different mass number. And we'll talk about that here. So remember, the mass number distinguishes isotopes. Isotopes just means different elements, or elements, but with differing number of neutrons. So mass number can help us distinguish isotopes. Atomic number will always distinguish an element. So for an atom of the same element, Z, our atomic number, will always be the same. Always be the same. So if the only thing that differs of the same element is the mass number, the only thing that differs is the number of neutrons. So for example, boron has two naturally occurring isotopes, boron 10 and boron 11. So you can see here in the two nuclear symbols, the only thing that differs between them is this boron has a mass number of 10. This one has a mass number of 9. So if we did our calculations, right? So, number of protons, number of neutrons, number of electrons for each of these different isotopes, we can see boron 10 has 5 protons, as indicated by the atomic number noted here. The number of neutrons is just the mass number minus the number of protons to get number of neutrons. So in boron 10, it's 5. In boron 11, it's 6. And then number of electrons, because this is neutral, number of electrons, number of protons must be equal to cancel. So 5, 5. So you see here, the only thing that differs between these two isotopes are the number of neutrons. So this showing you isotopes actually is an example of where Dalton's initial atomic theory breaks down again, because here we have atoms of the same element, but they aren't identical to one another. They are actually slightly different. And what we'll learn as we go through the rest of this course is it's electrons Electrons help determine chemical properties of different substances. So isotopes of the same element typically have the same chemical properties. So that's why we talk about, like carbon 12, carbon 12, which is the most abundant carbon, or carbon 13 dating, carbon 14 dating. Those are other isotopes of carbon, but the only thing that's different is the number of neutrons within that nucleus. Okay, so let's do one example problem, and that covers history of atomic structure. So let's write the isotopic or nuclear symbol for this specific atom. So this atom has 38 protons, 49 neutrons, and 36 electrons. So this first question, what element does it represent? So the element is dictated by the number of protons. So all we have to do is look at our periodic table. Which element has 38 protons? It's strontium. Okay, strontium right here on my periodic table has an atomic number of 38. So this is strontium. All right. So now the next question, is this a neutral or a charged particle? So neutral, since this has 38 protons, it would need to have 38 electrons in order to be neutral, but it doesn't, unfortunately. So we have an unequal number of protons and electrons. So we have 38 protons, 36 electrons. So if we kind of think about how those charges will cancel out, just think each proton is a positive charge. So we have a positive 38. Each electron has a -1 charge, so we have a -36. So if we think about bringing those two things together, there is an overall +2 charge. So this would be an ion because its overall charge is +2. All right, finally, let's write this isotopic notation, or the nuclear symbol here. So I know it's the element strontium, right, and that has a atomic number of 38 because it has 38 protons. And then now we need to figure out what its mass number is. Mass number is number of protons plus number of neutrons. That's where all the mass of the atom is. So those number of protons and neutrons are given. So it is 38 protons plus 49 neutrons. So if you add that up, that is 87. So that is its mass number. So that goes at the upper left-hand corner. Its mass number, number of protons, number of neutrons. And we would be done if this were a neutral atom. We would just put a 0 charge in the corner to indicate that it's a neutral atom. But in this case, it's not a neutral atom. It's an ion because the number of protons and electrons are different. So instead of putting a 0 for neutral, we're going to put that +2 charge for to indicate the total charge of the ion, because there are less electrons than there are protons for this particular ion. And so that goes over history and some nuclear symbols of atoms. Next, we will talk about molecules and atomic masses.